I'm Zhang from Team China, and today I'm going to do the report of problem number 11, that's self-assembly. First, let's review the problem. Put a number of identical hard regular shaped particles in a flat layer on top of a vibrating plate. Depending on the number of particles per unit area, they may or may not form an ordered crystal-like structure. Investigate the phenomena. Here's the keywords I define. First, for a particle, I define as characteristic length about millimeters, which means the number is about thousands. And for flat layer, I define the system as a two-dimensional system. And for ordered crystal-like structure, I define for the lattice structure and the orientational ordering structure. And here's the basic parameters I define. For the vibration intensity is for the maximum acceleration over gravity, and C is number of particles per unit area, and the filling fraction denotes for the proportion of all particles area and the area of the total plate. And here's my concept today. First, I will go through my experiments to introduce key phenomena. Then I will first introduce self-assembly of rods, and then the self-assembly of spheres and regular polygons. First, let's see our preliminary experiments. It's our experiment setup. This is the camera, this is the vibrating plate, and this is the base that makes sure that plate won't tilt. This is the power amplifier and signal generator we use to generate signals, and this is the particles we used. And first, let's see the two videos and look at the phenomena. In the left side, you can see that rods on the plate, and it finally forms the all structure, and the right side will finally form the lattice-like structure. And First we do the self-assembly rod. We find only in picture 2 it formed the ordered crystal-like ordered orientational structure, and the rest we didn't find is formed the non-isotropic phase. And for the self-assembly of spheres, when we add the densities, it began to form the lattice structure. If the density is very low, it is not a lattice structure. And here we analyze the key phenomena. First, the higher the number of particles per unit area, the easier it is to form an ordered structure. And the greater the anisotropic particle, the easier it is to form the ordered structure, shown in this graph. And let's see the self-assembly of rods. First, what is self-assembly? Self-assembly is a process in which a disordered system of existing components forms an organized structure or pattern as a consequence of a specific local interactions among the components themselves without external direction. And in this problem, it's a kind of static self-assembly, which means the ordered state forms as the system approaches equilibrium, reducing its free energy. First, let's consider a self-assembly rod is similar to the isotropic nematic transition in liquid crystal. For nematic, it means the orientational ordering structure, and for isotropic, it means non-ordered structure. And let's see the physical image of it. I analyze the entropy of the system. If we add the density of the system, actually the entropy will become larger. But for the nematic system, the extrude area, showing this yellow area, is far less than the isotropic phase, so the entropy will become smaller. And as two phases are competing, if the entropy will still be getting smaller, it will cause a phase transition, which means the system will form the nematic phase. And so, begin with van der Waals gas, consider an anisotropic arrangement. I construct the free energy of the system. And the FA is distribution function, A is orientation rods, S is exclude area for each rod, and the density parameter donates for the production between the filling factor and the length width ratio of the rods. And for the FA sacrifice normalization condition, and the free energy will reach its minimum value in the equilibrium state. So we may obtain the self-consist equation of FA. But it's hard to solve this equation, so I now introduce the variational method I use. I put the true function showing this formula. The graph is like this, well, alpha is variational parameters. So expand f at infinity, we may get the formula like this, and let's see free energy being minimum, we finally obtain the variational parameters. And then begin with the free energy, we get the equational state and the chemical potential for the nematic phase. And for the isotropic phase, free energy is easy to get. We may also obtain the equational state and chemical potential. So, using the phase equilibrium conditions, we may obtain the equation of the density, and we get the density parameters before and after phase transition, and we may obtain the critical phi density, which means that if the density is larger than that, it will form a nematic phase. And for experiments, I define the orientational order system by measuring the order parameter defining this formula, where theta denotes for the angle between each rod's orientation and the average orientation. For this graph, it's an orientational orbiting structure, x is close to 1, and for this graph, x is close to 0. And I also managed to analyze the photo using Mathematica, and this is the histogram I draw. And first, I measure relaxation time. I prove that as long as the vibration rod is obvious, the gamma won't affect the order parameter when stable, and the relaxation time is about several minutes. And I change density parameters and measure the order parameter, and I find the phase transition point is about 5.4, and it's in the excellent agreement with my theory. And next, let's see the self-assembly of rod-like particles. And first, I define the C as the number of particles per unit area, and the filling fraction is also for the proportion of all particles area to the place hole area. There are different kinds of phases for this system. First, when the filling fraction is very small, it forms the fluid phase, which means a non-lattice-like structure. And when eta is getting larger, it begins to form a hexagonal phase, which means a quasi-periodic crystal-like structure. And finally, when eta is large enough, it will form the solid crystal phase, which means all of the spheres was locked by the adjusting spheres and will form a lattice-like structure. And the fluid phase, using the method of canonical ensemble and the cluster expansion, we may obtain the equational state and chemical potential of it. And for the solid crystal phase, particles are strongly correlated, and using the molecular dynamic simulation, we may get the equational state, and where eta Cp denotes for the filling factor when close packed. And we draw the graph for the equational state, and we found that these 2 points, eta and eta f into s, which means when filling fraction is larger than eta s, it will form the lattice-like structure. And for these experiments, we measure lattice structure by the radial correlation function RCF, defining this formula, where the average is for each particle. And this is RCF for regular lattice. All the p's means the lattice structure. And if we measure the GR at R equals the lattice constant, we may conclude that the larger the GA, the closer to ideal lattice structure. Using the Mathematica, we may capture each center of each ball, and we may draw the radial correlation function. And for example of quasi-periodic crystal-like structure, if we draw the radial correlation function, we may find the GA is much smaller than the previous one. And using the viral EOS and also use the radial correlation function, I can verify my theory of the equational state. I plotted all the data here, and it's in an excellent agreement with my theory. And when we found at the phase transition point, GA is about 6.5. And for the phase transition, we also managed to find the Lindemann ratio, which is proportional to the mean square root of each particle's area. And we draw the graph here and find the system condensates about eta c is about 0.71, and is in excellent agreement with my theory. And we also managed to measure the coordinate number of a whole system using Voronoi mesh. And here's a photo analysis. I found that coordinate number is about 5.7, which means that the lattice forms a hexa-like structure. And for this system, I also managed to measure the effect of temperature. I use the vibration plate that can accurately control the acceleration and let not be tilting. And for when eta is about 0.53, I draw the phase diagram and found that at the yellow area, it formed the fluid phase as I predicted, but as the green area, it formed the solid crystal phase. It's an explanation of it, as the plate is not always ideal. The effective potential there will be some effective potential caused by fluctuation, and if the vibration causes the F external on each particle, and some particle may move to each other, which will cause the local density to become larger, and also due to the friction and dispersion, friction and collision and some dispersion, it will form the crystal island. But if X external is too large, the system will form a statistical equilibrium, which means no crystal island. And I draw a phase diagram for that. I found that in a certain region, the system formed a crystal island structure, and in the rest of the region, that the system will not form that structure. which that when gamma light spore begins to vibrate, they make this solid crystal phase, and I explain it. And rest for self-assembly of regular polygon. The shape of regular N polygon is similar to sphere, so the critical failure fraction is about 0.7 or a bit smaller than because of the anisotropic of each particle. And I use GA to measure the phase transition. As the particles are not the number of very large, in these experiments, I change eta is about 0.71, and I found GA is about 7.1, which is close to the theoretical value I predicted. And now let's go to our conclusion. So for the self-assembly of hard rods, the theory model, I began with a canonical ensemble, and I constructed the free energy and derived by myself. I can get the phase transition of it. And the definition of all the parameters is as is began to close to 1, and the critical density, which means the critical number balls, can be written in this formula. And when C is starting with C star, it will form the orientational ordering structure. And C star is also not affected by the temperature. And for the self-assembly of spherical particles, when vibration is strong enough, the definition of the lattice is that using the radial correlation function, as the lattice constant is bigger than 6.5, and you can also measure it by Lindemann ratio, and the critical density is 0.72 over pi r squared. When C starts with that, the system will form the Heisenberg structure. And for regular polygon, the critical density is about 0.7 over eta star is about 0.7. And when vibration is weak, only in certain range, which determined by the vibration parameters, that the system will form the lattice structure caused by the local interactions of the plate. And here's my reference. And thank you.
Thank you very much. So this was the report from the team from China, and now we have time for the opponent to pose questions. So please, Team Switzerland.
So what kind of shaker did you use in your experimental setup?
We both use horizontally and vertically. I can show
What kind of shaker was it? Was it a loudspeaker or?
A loudspeaker and also a vibration.
Okay, thank you. Does it move in a sinusoidal curve?
What do you mean?
Does it move in a sinus curve?
Yes.
Did you verify this experimentally?
It doesn't affect my experimental results.
Very briefly, what are the different phases you observed in using your setup for the balls, spheres?
Fluid and crystal.
How do you define these phases?
I use the radial correlation function.
Okay. What mass did your particles have, both the rods and the spheres?
For the several milligrams to several grams.
So to your measurements, are you saying you tracked all the different particles?
For the static, when it's static, I track all the particles, and when the particle is all moving,
did you track particles over time as well?
Yes.
How do you quantify? Did you quantify the entropy in your system?
I explained it in my physical image page. I can discuss it with you later.
Can you quickly go to slide 18, please, to the team?
Slide 18.
18, yes. So can you very briefly explain to you what is alpha?
What is a variational parameter in the true function?
What does it describe physically?
Physically, that the anisotropic of the system.
So, how long did you wait to see if you could achieve a stable state?
Several minutes.
Several minutes. Did you vary the frequency and amplitude of your shaker?
Yes.
Did you always have only one nuclearization point with the spheres?
Same. If you change that, the vibration in a certain range will not.
Okay, thank you very much. The time for questions is over, and now there is the time for preparation of the opponent for the opposing speech. Thank you.
So, yes.
Okay, so the time for preparation is over, and now you have time for your opposing speech, please.
So, hello and welcome to my opposition on problem number 11, flat self-assembly. Let's quickly do the outline of the task. This was well covered by the reporter, and I believe he did a thorough investigation of this phenomenon. As this is a current research topic, I'd like to start off with a review of some recent research. First of all, Mr. Rice, in his paper published in Physical Review Letters, had this plot where he nicely plotted the Lindemann ratio against the filling fraction and was able to show that it rapidly decreases for a certain filling ratio. On the other hand, Olafsson and Urbach, in their also public publication in Physical Review Letters, were able to show for a spherical system that we are able to observe three phases, two of which were also shown beforehand, and that this also depends strongly on the packing density or the number of particles used. Also, they introduced the critical frequency we need, which allows or differs whether particles are able to hop over each other or not. And finally, in this paper, also from Physical Review Letters, using sticks or rods, we're able to see that the order clearly increases with the filling fracture. So overall, the reporter was able to reproduce and confirm many of these results, and with this also gave us deep insight into this phenomenon. Quickly to the outline of this report now. The phenomenon, in my opinion, was not well demonstrated with the videos. It was hard for me to follow what the different phases are, especially with the rods. The qualitative theory was hard to follow. Why exactly do these nuclearization points form? Why exactly do we have such clusters? The quantitative model was decent and applicable. However, it was hard to follow where these formulas come from and how exactly it quantifies this system. The experiments, yes, were okay in my opinion. The analysis, however, could have been more in depth. Why does it fit so well? Why doesn't it? But finally, the conclusion was through and gave us a nice summary of the report. Quickly to the theory. So he defined all the variables. This was very helpful in the beginning. He explained what flat self-assembly, or self-assembly as it is actually, is defined as, and he gave a definition of phase transition. However, there was no qualitative explanation for why we find these nuclearization points. Some critical parameters were not varied, in my opinion, amplitude and frequency, two of them. And the critical frequency, which is needed for certain phases to appear, was not introduced or explained well enough. So to the experiments, he used different shapes. This is a very strong point. It behaves very differently, of course, depending on the shape of the particles. And also, the the packing density, which is explicitly mentioned by the task, was varied. Also, the angle of the rod, in my opinion, is a very good measure to define how ordered our system is. However, I'm not sure how accurate a membrane speaker is for a sinusoidal wave, and this was also not verified experimentally. Also, exactly how his data was acquired was unclear, but I think I'll come to this later on in the discussion. And with this, I would like to ask the reporter to come on stage.
Okay, thank you very much. So now we continue with the discussion between the opponent and the reporter. Please.
So very briefly again, you use different particles. Let's start off with the most simple one, the spheres.
Okay.
So you said you have two different phases.
Three.
Three. Could you maybe repeat?
Maybe two we can observe, and the third in a very short range.
So can you please repeat for us how exactly do you define these different phases? Fluid, solid, and transition.
Okay, please change to slide 30. And we use a radio correlation function. This is for the...
Please be sure the microphone, because especially for the live stream, if you don't use the mic, they don't hear anything.
Okay, we use a radio correlation function to measure it. And if you measure the GR at the lattice constant, if it's 0, it is 1, it is that fluid phase. It's very high.
So in your transitional phases, you mentioned a transitional phase, which we have of course. How exactly does the spectrum look on a transitional phase?
It will is that for the periodical crystalline structure, and this is for the lattice structure. As the transition point will be about 6 to 7.
So on the lattice structure, we have a clear peak for 1. This is of course the direct contact between them. Can you please explain to me why we have one just before 2?
One just before 2, that the ore peaks is either at about 1 square root of 3 at 2 square root of 7, or because that the triangles which the integer length about m and about, or about just...
Yes, so maybe when we have a hexagonal structure, which length will this be? Square root of 3.
Square root of 3.
Okay, yes, I fully agree on this. So, you mentioned your different order parameters, correctly?
Yes.
So with this, I'd like to move on to the how you measured and acquired your data. So first of all, to come back to your shaker, maybe the team member could go to the setup picture. So did you, once again I'd like to ask, did you confirm that your shaker it moves in a nice sinusoidal wave?
I changed the wave function during the experiment, and
so do you think the signal we input into your shaker is the actual signal of the movement?
Yes.
The accurate shaker. Okay.
In further experiments to find the effect of temperature, I also use a very accurate vibrating plate that is about 1 kilograms weight, and this is the controlling.
Yes. Thank you. So when you filmed, or I believe you filmed your setup from above.
Yes.
How many frames per second did you have?
Frames per second
on your camera?
About 240.
So for every single frame, did you try to measure what your distribution was?
Oh no, I just to measure that for one. I thought it was stable, and for the few points, and I also measured the error bar of the.
So you selected a few frames and a few points which you then tracked.
Not few frames, just few seconds. These minutes or 10 seconds after it, or just.
And in this period, you looked at all these single spheres to be completely sure that we have the overall system which is being described.
Oh, for the Lindemann ratio, I measure it, but for the correlation function, I didn't measure it. Correlation function needs to be measured.
So you have a container here, correct?
Yes.
How does the container affect the system?
An edge of it. That the area of the system being limited.
Did you maybe observe that we have nucleization at the edge?
If the plate will be tilted, it will have the nucleization at edge, like.
Yeah, of course. When we tilt it, we'll have nucleization at the edge. But did you also observe this in a non-tilted case?
Until I make sure that all particles will not move in a single way. That was not tilted.
So they don't move in a single way?
Yes.
So maybe you could go to your phase diagram now.
Phase diagram for frequency.
For the exactly frequency dependency. So maybe while your teammate does this, could you please, what do you think are the three most important parameters of this system? When we keep the particles constant, of course.
Most important is the filling fraction. That if the plate is ideal, there will not be any the function potential, that the frequency and the vibration density won't affect the system at all, but that the plate is not ideal.
Frequency doesn't affect the system at all?
In ideal condition, but it's not ideal condition, it will affect it.
And so maybe I disagree here. Why do you think the frequency won't affect the system? Did you verify this experimentally?
I changed that all blue dot is nearly form a crystal-like island structure, and for the white dot it didn't form like. And if I change the density, the more the density is equal, is near to the 0.7, is the area.
But so here I can clearly see the regime gets larger when we vary the frequency.
Yes. If that the eta is larger than 0.7, that will be the whole ground will be the green. If you like the it's obvious.
In this phase diagram here, we can see the red points diverge together,
yes.
The transition. So from a certain frequency, we won't be able to observe this solid state at all.
Perhaps for something like that 90 hertz, that may matter.
So maybe quickly to be very clear here, we have three different phases here,
No,
I believe.
No.
These are the red points, correct? And these are the blue ones in here? There's no line here, then why are the points on the left of that phase?
All the red is the same point, and only in the frequency and the vibration density in a certain range that I may have a qualitative explanation on my theory.
I know that would be fine. So the red points, no, please go back.
I'll go back.
The red points were points where you had fluid state or gas state.
Fluid, or just.
And the blue ones were ones where you had a crystal-like structure.
I use pH merit so that the definition between you, if you see it, you cannot clearly identify it by your
So you also showed in your videos, I believe, or we know there should be a phase transition.
Yes.
Where we have both fluid or gas as well as a solid structure. Where in your phase diagram would these appear?
Fluid and gas, I believe that for both fluid and gas it's same, that which means disordered structure. I don't identify the fluid and gas it's also being the red dot, and I don't think it's necessary.
You think they're also red dot?
Yes. It's necessary to identify the plate. The problem statement asks us to only investigate the crystal phase.
No, the problem statement told us to investigate when and when not we have a crystal phase. So I believe the transition phase is actually a very important part of the
if I investigated, the green region is transition.
So did you observe any hysteresis?
What do you mean?
So does it make a difference if we move to the crystal from above or below to the transition phase?
From this, it's not a lot of difference between.
Yeah, but during your experiments, did you generally start out with a high vibration intensity and then go down?
I don't change the direction of it. I just find the plots and the low vibration density and the high vibration intensity, which means that the phase will not vibrated or vibrated obviously for the certain frequency.
Okay, so what you did is you chose a certain intensity and frequency, and then you plotted that point.
Like this way. This way.
So you moved from bottom to top.
Yes.
So do you believe we could observe a difference going from top to bottom?
I don't think so. And from also such a point, I just tried in experiment and I didn't find something other changes in the phase diagram.
So very briefly, for my last point, what is discussed and not yet explained completely is, of course, the translation of the vertical direction to the horizontal direction.
Okay, I also changed but for the horizontal direction, you need very large power to let the sphere move, obviously. So I not always use it, so my...
Yes,
my
but generally we're pushing our particles in a vertical direction, correct?
No, the difference is very small. That you see the square dot and the black dot in this diagram.
But so qualitatively, why when we vertically oscillate our system, do the spheres move in a horizontal plane, which is what we're, in the end, we are measuring?
Because that's the unideal of the plane. It's not the horizontal, ideal horizontal, that will have some fluctuations. So the particle will move horizontally. And for the vibrating, in my opinion, the vibrating only gives the system a temperature, not for the horizontal, no vibrate, no vertical.
Thank you.
So the time is over. Thank you very much for the discussion, and we have 1 minute of summing up of the discussion.
Okay, in that case, we'll now summarize this discussion. Generally, we talked about 3 points: the what we see, the how we measure and see it, and finally the when these phases occur. So, what we have in the whole system now, we have 3 different phases, or one which is a transitional phase, which was quantified using a parameter. And I believe the transitions were not investigated well enough, especially in the phase diagram. We then discussed the experimental setup, and I'm still not sure we have a perfect sinusoidal movement, and this should have been verified. The most important parameters mentioned by the reporter were the frequency and the filling ratio. In my opinion, the amplitude is also a critical parameter here. Exactly. Finally, we discussed the phase diagram, especially the transition phases, and we had a discussion whether there could be high hysteresis. However, the reporter did not observe this, so that is that. Thank you.
Okay, thank you very much. In the next phase, we have the question from the reviewers.
Okay, the first question to the reporter. Have you ensured that no gladney figures occur on your membrane?
Please.
Have you ensured that no gladney figures occur on your shaker or on your membrane? Yes or no?
I don't understand the question.
So this means that the acceleration is constant over the whole surface?
No, because of fluctuations, that all particles all give the random move.
Okay, then I disagree with this because this should be important. Do the opponent agree that this is valid for its experimental setup to not ensure that the acceleration is constant?
As stated before, I don't believe this setup was verified as to be accurate in this.
Yes, okay, I agree with this point. Then could you go to slide 8? Firstly. So,
You can ask your question.
yes, how have you ensured that this is a two-dimensional system? What have you ensured that the particles don't overlap themselves?
Two-dimensional system, the part I consider as two-dimensional gas.
So how have you realized this experimentally?
It's just move along the plane that you can see as a two-dimensional system. I don't think.
Okay, I discuss on. Then I go to. Could you go to slide 42? And first I ask the question whether wall effects are important in your case. Because here we can see on the white picture that at the end to the wall we have other phases. Now could you show the picture again?
A picture again. Okay.
So as you can see in the picture, in the middle we have other phases than in the end. So are wall effects in your case important?
I only give the explanation that the crystal island could be formed, and if we larger the intensity, it will be.
So okay, now so this opponent, do you think that wall effects should be considered by the reporter?
What effects?
Wall effects.
Well, as he didn't observe nuclearization at the walls, I don't believe this is important.
Okay, because this could also maybe be seen here. Then next, to the reporter, how did you determine your effective temperature used in the theory?
What?
How did you determine your effective temperature you've used in the theory?
The temperature.
Yes.
It's necessary. If the vibration is obvious, it's a non-thermal system. The temperature is actually a non-relevant parameter.
But it was included in your theory.
Yes.
So
I
how did
needed
you determine it to now give a theory?
I use KT equals to IME squared.
Okay, then I go to the next point. And then, can you observe other phase separations, for example, now in this case, if you consider them?
What phases?
Phase separations. So you have different phases in different regions.
Different phase diagram. What do you mean? I do not understand.
Now I go over to the next point. Is a phase transition which occurs at first always the same for all different particle shapes?
Yes, different particle shapes.
Okay, I clarify this later. Then can you also observe this static structure for all shapes?
For all, For the Ross polygons and the severe particles, I also.
So what does the opponent think?
Very quickly, because we
Can you
are
repeat the question very quickly?
Sorry, because the time is over. Thank you very much. So we spent the time for questions from the viewer, and now we have the time for preparation of the review of 2 minutes. Okay, the time for preparation is over. Please, can you start your review?
So hello, I'm Bećić from Germany, and I lead a review on problem number 11, flat self-assembly. First, let's take a look at the report. The first here gave a clear definition of the order parameters, but still he didn't give a credible explanation what they now really mean and what they describe. Next, he also modeled the microscopic dynamics using the effective Brownian dynamics and now the density functional theory. Even if in this case he didn't now determine the temperature theoretically, what was not clear. Then also he used a literature simulation to calculate these order parameters, even if this was not totally correctly cited. Next, it was unclear if his microscopic equilibrium was reached, and maybe several minutes might not be totally sufficient to reach now this equilibrium. Next, he also gave the experimental statistics were improvable, and it was unclear whether the oscillation was homogeneous over the whole plate. As in this case, if exactly figures occur now here standing waves on this plate, now the acceleration is no constant, and this could also lead to ordering, and he couldn't ensure that this isn't the case experimentally. Then he also stated there is no difference in dynamics for spheres and polygons, what is also very doubtable, and he didn't give this. So next, go to the opponent. He asked reproducibly of his experiment, especially of his acceleration of the phase. Next, he also questions the static case in this experiment when it was reached, and he also recognized the lack of the arm contribution and criticized the unclear qualitative explanation. Next, he also clarified he didn't clarify the temperature, but it's a really important part in the theory, as this is now the transition from his basic mechanical system to his effective thermodynamic system. Next, he also stated that the frequency and the amplitude were not varied. And then what is also false, as he has done this. Next, he also gave a too small focus on his own report, as he presented literature in his presentation. He didn't focus on the report of the reporter. And he also didn't question the definition of the irregular shape, what is even mentioned in the task, and it should also be improved by the reporter. And next, if we now go to the key point of the discussions, firstly, it was discussed the definition of the phases, the fluids phase and gas phases. And here first the opponent stated he asked for a qualitative explanation and he didn't gave here an own opinion. Here the reporter repeated his qualitative definition of his different phases. And here our opinion is the opponent and the reporter should have explained this phenomenon qualitatively as it is ensured that the entropy has to be maximized, and as a result some degrees of some translation and degrees of freedom, orientation and degrees of freedom can be compensated by the win of orientation and degrees of freedom. Next, if we take a look at the measurement of the order parameter, the opponent asked for experimental details, especially the frame rate and the signal. And here, the reporter stated that not all particles were tracked, and the frame rate was also unclear. And here, also the signal versus time, there were not exist any calibration. And here we say, in our opinion, it should be discussed whether experiments took place in a theoretically assumed equilibrium, that what was missing, and still also all particles on the surface should have been tracked to get now really additive and good reliable statistics. Next, if you go over to the most important parameters, the opponent disagreed that the frequency is the most important and he asked for hysteresis. The reporter stated that the frequency of the shaker is not important and that he didn't observe any hysteresis effects. And here, in our opinion, we agree to the opponent that the effective temporal changes with frequency and acceleration, and as a result, also the phases change. And the acceleration should be inversely instead of the frequency. And now to summarize, if you take a look at the task, it is a very, the phenomenon is in this case very rich. There's a case he also realized the indefinite definition of the two-dimensional flat layer. He investigated what is spheres and what are no regular straight particles, and he also investigated structural, crystal-like structure by the order parameters, and he also gave a quantitative approach only from literature.
Thank you much. Okay, concluding remarks of the opponent. I think your mic is there. I don't keep your mic.
Okay, first for the works I've done in this problem for the phase condition class. This theory is all derived by myself. I constructed the free energy, and this can be now found in literature. I think it's my biggest own contribution in this problem. And for the relaxation time in this problem, I measured it's about several minutes, and I think I'm waiting for about 5 to 10 minutes. That is necessary. And for the difference between the sphere and polygon, this has been done very detailed in the literature, and this is a phase diagram for it. You can see as the n become larger, that the eta limit n become infinitely eta is about 0.72, and it's equal to the sphere's temperature. And for the effect of temperature, I also changed the frequency and the amplitude and draw the phase diagram, and I gave a qualitative explanation of it using qualitative explanation of it. And now I'm going to repeat my conclusion that for the self-assembly rods, as I constructed the whole theory and derived it by myself, and I get the critical density of it, and it's a non-thermal system. We can find it from the older parameters. And for the self-assembly rods, as the all vibrational rods is enough, these will form the lattice-like structure, and the exact definition of lattice structure as using the radial correlation function, as the lattice constant is larger than 6.5, as in the EOS, as in the equilibrium state. And for the one vibrance weak, I also investigate the frequency and the amplitude of it, and it may form a lattice structure caused by the non-ideal of the plate.
Okay, thank you very much. Five minutes for questions from the jury. So reporter, opponent, and reviewer are ready. I've seen jury is ready. So Ilya was the quickest one, please.
Okay, to the reporter, your slide 33, you talk about the radial correlation function. Yes. And I'm wondering if this is experimental or based on simulation, and then does this apply to your entire system or only to the small island where you observe the onset of positional order?
It is to the whole system. In this experiment graph, I capture each center of the ball and I draw the radial correlation function using MMA.
Is it experiment or simulation?
Experiment.
Okay, thank you. John?
Can I ask the opponent, please, what he believes the hysteresis effect would be?
I believe it can make a difference where we'll have the phase transition depending on whether we go up with the frequency or amplitude or go down. And the opponent here only, of course, went upwards using with his temperature, and maybe there could have been a difference in the phase transition. Difference meaning in the position of the phase diagram.
Okay, thank you. Andre?
To the reporter, could you explain how the strictly vertical vibrations leads to rearrangement of particles in horizontal positions?
Okay, I think it's caused by that the plane is non-ideal. It may be not horizontally, and if that the vibration will cause a vertical force exert on each particle, and it may transfer, it may move horizontally.
Okay, Peter?
So for your theory temperature, the effective temperature is clearly very important. How did you compute the effective temperature for your system?
The temperature, if the plate is ideal and all the particle is ideal, no dispersion, I think temperature is lesser. It's not important, but for that real condition that I measure temperature using this, but it's
how did you compute it? I don't want to know
change
why.
the vibration intensity, which means change the.
But what is the formula for it? Do you have a formula for it that relates the vibrational density?
A formula you can kT equals mv squared. You can define temperature, but it's extremely high. I don't think it's necessary for us to discuss it about it.
Okay, Kent?
To the reporter, your variational parameter alpha, is that experimentally determined, or is that?
No, for this I guess the true function like that, so I construct it like that. I think mathematically, true function alpha. It's just a mathematical method for I to solve the critical density for it.
Maciek?
I have a question about experimental setup. How it vibrates your plate? It means how it vibrates borders of plate.
Borders of plate.
Put the plate to make sure that all plate won't tilt together just in its two-dimensional system, and make sure the plate won't tilt and like vibrate.
Yeah, so it means that also borders are vibrating.
Yes, ball is vibrating.
Okay, Konrad, I think I start first with the jurors which did not have the question yet, and then if we have time, continue to the jurors which already had one.
The question for the reviewer, do you think the amplitude of the oscillation also affect the phenomenon?
You mean the peak acceleration used, or the amplitude of the
amplitude of the oscillations?
Yes, I think it has also an influence as it influences his effective temperature, so the excitation is a result out of the ordering as in his.
So the same question for the opponent?
I agree that the amplitude should be important and should be listed.
Okay, sorry, next question, Maria.
To all of you, starting with the reporter, do you believe that the material of the particles is an important part of this phenomenon?
If the vibration is obvious, that it's not relevant, it's not important, but for that, you know that if the vibration is not obvious, that some particles are moving, some are not, it's important because of the friction and dispersion. That in the phase diagram you can see that the green region is strongly correlated to the temperature end.
Okay.
Yes, the material will affect the coefficient of restitution, and off-centric collisions are actually what cause the transversal movement.
Okay, thank you. And we have a quick question by John. And sorry.
This question is primarily for the reporter, as I don't think we'll have time to move on from that. Spheres roll, the hexagons can only slide, and the rods can roll in one direction and slide in the other direction. So how might this have affected your experiment?
That only, actually only the move will cause the phase transition. If they only rotate, it won't cause a phase transition, I think. A two-dimensional system.
Okay, and the last question by Ilya. Quick one.
I think we're out of time, yes.
Okay, if it's your decision, then I can live with it. So thank you very much. Thank you, reporter, opponent, reviewer, and yeah. Now we have time for the jury to put their grades. We have a rather complicated score sheet to fill in, so we will need a couple of minutes to do so. So please, can I kindly ask you to stay quiet now and give us a chance to work, as you have brilliantly given the chance to work for the team. So give us a few minutes to finalize our work here. Grades for the report. Now, starting from myself, 7 6, 6, 7, 7, 7, 7, 5, 6, and a 6. Grades for the opponent. No. 6, 8, 7, 8, 9. Undefined. 8, 9, 6, 6, 7. And grades for the reviewer. No. 7, 9, 8, 9, 8, 9, 6, 7, 7, 7. Thank you very much. Okay, so let's start. Okay, for those who don't know, now we have the part of the game where the jurors have to explain their decisions. And yeah, very clearly there was a single 5 by Peter. So could you comment a little bit and then add also your partial points for the grade number 5?
Yeah. So I thought a long time how to evaluate this report. I think it was a very challenging problem. And for me, the biggest problem was that the basics of the theory were not clear to me. So for me, it's not even clear that you can use an economical example here, because I think you didn't make it clear that this is an equilibrium system. So, in my opinion, and I also know what temperature even means in this case, because when you model these things as hard spheres, there's actually no energy. There's a temperature usually tells me how I should evaluate states based on energy with the Gotsmann factor. And this is completely unclear to me how this works in the theory. And when I ask you how temperature is defined in the system, you gave me an answer that I didn't understand. Maybe this is because of me, but I cannot evaluate the theory as well if you didn't give me this, at least from your communication. It couldn't convince me that your theory is valid. And therefore I also have difficulties to believe the experimental and theoretical correspondence. And also I think that the boundary conditions, they sometimes seem extremely important, that I also couldn't see how they go into your theory. Yeah. So eventually I ended up with 5. Yeah.
Okay, can you also tell us the partial grades?
So I gave you a 2.5 on the report because of the things I mentioned. A 1.5 on the discussion, and I subtracted 0.5 points for the
Okay. Okay. Thank you much. And there were 3 7. So let's say very brief comment by Ilya as you're close there.
So my grade was the highest one?
One of those.
One of the highest. Okay.
I believe I don't have the names there, but you gave a 7.
Oh, okay. So first of all, I liked your report, but your report had a lot of shortcomings at the same time. I very much agree with the remarks with Peter. It's just a question of putting an adequate grade on a consistent scale. I felt that among your strong sides was the amount of work and the depth of your understanding and the depth of the critical analysis. Also, your experiments were very interesting. But on the negative side, I very much agree with the remarks by Peter. I also think that it is a big problem that you were presenting a lot of empirical results and theoretical results and experimental results at once, and at times it was difficult for me to understand what is your what is the literature-based value, what is your experimental value, what is the value that you calculate yourself, and what is an empirical assumption.
Okay, maybe if you can mention also the partial grades then briefly.
Okay, my partial grades are 3, 3, and 0.
Okay, so that sums up to 7. Thank you very much. For the opponent, we have, please be very brief, because there we have 4 times a 6, so maybe very briefly, Andre? The 6, yeah, you.
6 for
opponent.
In my opinion, this was a usual position, so 6.
Yeah, maybe I could add that, like, I subtracted you points for time management, because I think like the literature overview at the beginning was very high, and let's say not really that much relevant to their report and a couple of other things. But Kent, the 9.
9, yes. I thought it was very good. Your questions, you asked all the questions that I had, including some that I thought probably going to be overlooked and that I would have to ask at the end. I thought you did a really good job of somehow getting through an incredible amount of material without seeming rushed. And I don't know how you managed that, but it was a very good.
So the partial grades?
Partial grades. I got 2 questions asked, 3 out of 4 for the speech, and 3 out of 4 for the discussion. Nothing else.
Yes, you can have concerning the reviewer, please. Your 6 is a single one lowest. 6 was the lowest one or the highest one?
No, 6 was the lowest one.
Okay. Just general remark. For the point, very briefly.
No, please, could you comment on the reviewer?
On the reviewer. Okay. The reviewer addressed the shortcomings in the report concerning the conditions in which the directional and positional order appear in the system, but at the same time I could not go too high towards very high grades because I think that your opinions were presented in a rush, and sometimes you were just presenting a lot of ideas without prioritizing, setting priorities. Which of them is the most important? My partial grades are 1 for questions, 2 for review, 1 for review of opposition, 1 for discussion analysis. And I think this was a good review, but still I could not go higher.
Okay, yeah, thank you very much. But Alan thought it's possible to go much higher, up to 9.
I think I need to put it in context of the whole fight. I went 9 because as we went through this, I started up with the reporter and I was very confused. It was very, very fast and I hadn't taken things on board. The opponent did a very good job of clarifying things for me, and the reviewer, which I gave 9 for, basically I've marked him down slightly for not giving enough time in the questions, that it's still a bit too quick in questions and not always making point. So that came down a little bit. I thought the review of the report was very solid and reinforced many things that the opponent had done, and added a few extra things about the acceleration that I thought was very, very relevant. The review of the opposition, they recognised the good points that the opponent had just done, but the prioritization, I've said, is reasonable rather than good, so that was a minor point coming down. And I thought that, well, there was some relevant parts in the discussion that were covered. I don't think it was fully conclusive. I didn't think there was anything particularly missed out. There was a few little points that I've already mentioned in the other area anyway. And because we can get up to a large number of points here, that sort of rounded off as a 9, even though I was taking things off in each place.
Okay, thank you very much, Alan. So let's have a big applause now for the whole round. And now we are a bit under time pressure, so we make, let's call it a semi-break. The teams need to change their tables, but once they are ready with changing tables, we immediately start the preparation time. So if you need immediately to go for a toilet or something like, please do so. We don't have more than a 5-minute break. There will be a big break after the second round.